Welcome to an introduction to Salience Theory, an alternative to prospect theory. In the past 60 years, a range of important violations of expected utility theory have been identified. Risk preferences seem to be systematically unstable. In real life, people participate in unfair gambles. They pick risky professions and invest without diversification. Yet at the same time, they buy insurance. In the lab, subjects switch from risk-seeking to risk-averse choices upon normatively irrelevant changes in the choice problem. See the Allais paradox. Simple prospect theory solves much, but it still has empirical problems such as people playing slot machines, which is risk-seeking in gains, and buying insurance, which is risk-averse in losses. Weighted prospect theory comes in as one alternative put forward to resolve some of the tensions of simple prospect theory. It matches lab evidence quite well, but not perfectly. André Schleifer and other co-authors propose a new psychologically founded model of choice under risk, whereby risk attitudes are driven by the salience of different lottery payoffs. You can see some of their important papers here. André Schleifer is mentioned because he is an important economist in other areas as well. He was born in 1961 in Moscow, teaches at Harvard, previously at Princeton and Chicago. As of May 2016 and also February of 2020, he was the #1 individual on the list of most cited scientists in economics and business. He won the John Bates Clark Award in 1999. He's known mostly within corporate finance and the economics of transition or development economics, but also within the economics of financial markets, and especially with deviations from efficient markets, or behavioral finance. What is salience? Salience refers to the phenomena that when one's attention is differently directed to one portion of the environment, the information contained in that portion will receive disproportionate weighting in the subsequent judgments. Salience is a property of stimuli in context, or reference dependence, this insight from Weber's law. Changes and differences are more accessible to a decision maker than absolute values. As an example, a change from 5 to 15 is more salient than a change from 9,905 to 9,915. Our attention will focus on the 5 to 15 more. It is more salient. The decision maker focuses on the most salient payoffs. She is risk-seeking when a gamble's upside is salient. She is risk-averse when the downside is salient. The agent focuses on the most salient state of the world. In the gamble, which payoffs are most different proportionally? What gets my attention? What is salient? The agent transforms probabilities into decision weights, with more salient states receiving a greater weight. Whatever has my attention will seem more likely. It will receive a greater magnitude of weight. The agent then computes the value of the lotteries using these endogenous decision weights. What should I choose based on my view of the probabilities and the payoffs? If we're going to set up the model, we have to first determine what is salient, losses or gains. We will need to know, first, our reference point, which we will label X. Second, the gain from the reference point if the gamble is 1, which we will label G. And finally, the loss from the reference point if the gamble is loss, L. The reference point X is very simple in these examples. X will always be the value of the sure thing alternative. So just in these examples, to keep things simple, we will use the reference point X as the value of the sure thing. In case you don't understand it, we can see a little bit of math here to describe how you would calculate L, but the basic idea is that it's the gamble's low payoff subtracted from the reference point. So as the last example on here says, if the gamble's low payoff is 45, and the reference point is 75, then our L is equal to 30. G is very similar. Again, we can work through the math. If you need to pause the video and look at what G actually is representing, you can. But basically here, we can look at that last example and see that if the gamble's high payoff, the winning payoff is 100, and the reference point is 75, then G is equal to 25. It's the difference between the high payoff and the reference point. So what you have to do is you have to determine what is salient, losses or gains, with what we have as our salience functions. So you need to be familiar with these two salience functions. What you do is you determine the variables that we have just set up, the x, the g, and the l, and then you plug them into these salience functions. We find the salience of our gains by having g divided by 2x plus g, and the salience of our losses by having L divided by 2x minus L. Once you have solved what the salience is in gains and the salience is in losses, then you take the absolute value of the salience function to determine if the loss or the gain is more salient. Here on top, we could see that the gains function is greater than the loss function, so we would say gains are salient. On the bottom, we have the g over 2x plus g. The absolute value of that is less than the absolute value of L divided by 2x minus L. And so what we would have is that the losses are larger in terms of absolute value, so losses are salient. When losses are more salient, the agent will underweight the probabilities of gains. When gains are more salient, the agent will overweight the probabilities of gains. When losses are more salient, you increase your risk aversion. When gains are more salient, the agent will overweight the probabilities of gains, and that increases risk seeking. Why would we consider salience theory over prospect theory or even weighted prospect theory? Well, a number of reasons. Salience can explain large shifts in risk attitudes independently of shifts in total wealth. The model also gives an intuitive account of shifts in risk attitudes without relying on the curvature of a value function. But most importantly for us, it can explain risk-loving behavior when gains are salient, even for moderate probabilities, which salience authors suggest this occurs at times, and weighted prospect theory won't handle it. So what we would see in this case is that perhaps salience theory can answer some of the limitations of weighted prospect theory, but the debate remains. In the article, Salience and Asset Prices, Schleifer and co-authors argue that salience theory helps account for several time series and cross-sectional puzzles in finance, including the equity premium. So perhaps where weighted prospect theory comes up short, or simple prospect theory comes up short, salience theory can help us kind of solve some of the puzzles that we have, and some of the important puzzles, including the equity premium puzzle. The model will aim to more accurately map lab results of choice under risk, provide an alternative to weighted prospect theory that is very similar, but perhaps more accurate in some potential important ways. That's the key takeaway here, is that there is debate, and salience theory is trying to put forward a step forward in the evolution of these behavioral models. In the following videos, you will get 5 mathematical examples in working through the basic start to salience theory. I highly recommend pausing the videos and trying to solve them on your own as soon as you feel comfortable with the process, perhaps once we get to the 3rd example, or example C.
Okay, so let's set up problem 1. All right, in problem 1, what we're going to do is we're going to say we have a probability of 0.95 at an outcome of $1. Or we can have a 0.05 chance at an outcome of $381. That would be our gamble, right? 5% chance at 381 and a 95% chance at $1. Or we can get a sure thing of $20. So a probability of 1 for $20. All right. We need to know our gain salience function and our loss salience function. And then what we need to do in order to solve these is we need to understand what G is equal to, what L is equal to, and what X is equal to. All right, so we go through and we can say, okay, the gains function, the G, we need to know X first. So if we want to solve G, we need to know what X is. X is our reference point. Our reference point is always going to be, in this approach, the sure thing. We know we could get $20, so that serves as our reference point. So we compare everything to the thing we know we could get, which would be $20. So we say X is equal to 20. And now we can solve for G. We can say, okay, if we got the good outcome, the best possible outcome from the gamble, 381, how much more is that than our reference point of 20? So how much more is 381 than 20? What's the difference between the two? And we get 361, right? And then we can go through and we can say the same thing for L, for our loss function. We can go through and say if we lost the gamble, if we had a bad outcome, we would get $1 in this case. What's the difference between our reference point and the loss outcome of $1? So the difference between 20 and 1 gives us an L of 19. All right, now what we can do is just simply plug this into our equation. We can take G, 361, divided by 2 times X. So we can say 2 times 20 plus G, which is 361, and that's our gain salience function. And then we can do the losses. We need L. L is 19, divided by 2 times X, which is 20, minus L, which is 19, and we have our loss salience function. You can punch these into your calculator and go ahead and do the math, and you should get an answer of 0.9002. And then for our loss salience function, you should get an answer of 0.9048. And then what we do is we take the absolute value of these two. They're both positive, so this is easy. And you see which one is larger. In this case, our loss salience function is slightly larger than our gain salience function. So we are going to be salient in losses. So it's going to be loss salient, and that will impact what we do next. So that would be loss salient within our loss salient function and gain salient function. We have determined that with this gamble, we're loss salient.
From the example in problem 1, the loss of 19 from a reference point of 20 proved to be salient when compared to the potential gain. It is important as you move on to problem 2 that you keep this in mind. Keep problem 1's example fresh in your memory, that the loss of 19 from a reference point of 20 proved to be salient when compared to the potential gain. The results from problem 1 were that the loss salience function was greater than the gain salience function, which when loss salience is greater than gain salience, loss salience will increase our risk aversion. This means that we're more likely to choose the sure thing. When the expected values are equal, which will be the case in our examples, and you have no other risk preference, the decision maker would choose the sure thing here. If expected values were not equal, we'd still see an increase in the chances of taking the sure thing as risk aversion is increasing. So we were loss salient, which increases risk aversion, which makes us more likely to choose the sure thing. Here again is the work shown from problem 1 for you to cover. In problem number 2, we have a loss of 19 from a reference point of 320. This proved not to be salient when compared to the potential gain. Compare this back to what happened in problem 1. Do you see how the loss could be salient in problem 1, but not salient in problem 2? In problem 2, the loss salience function's absolute value was less than the gain salience function's absolute value. So gain salience is dominating here. So gains are salient. So gain salience increases our risk-seeking behavior, and we're more likely to choose the gamble. Again, you can see the work from problem 2 shown here to work through the math. In your comparison of problem 1 versus problem 2, you should note that in both cases there was a loss of $19, but the loss of 19 in gamble 1 is far more salient because it is being compared to the sure thing of 20. In gamble 2, the loss of 19 is far less salient because it is being compared to the sure thing of 320. The proportional loss in gamble 1 is much bigger than the proportional loss in gamble 2. The salience of the loss in problem 1 increases risk aversion because it is salience in the loss. You see a big loss because the proportion of the drop from 20 to 1 is so massive. When compared to the relative salience of gain in problem 2, we see we get risk seeking. No longer is that loss of 19 so salient because it is a drop from 320 to 301. This increases our risk seeking because the gains now look more salient. Problems 1 and 2 have actually been used in experimental settings. Problem 1 showcased in the experiment 83% of the subjects choosing the sure thing. In problem 2, only 35% of the same subjects chose the sure thing. So we have the same people, but problem 1 showcases salience in losses, and problem 2 showcases salience in gains. In problem 1, we should expect to see more risk aversion, and we do. And in problem 2, we should expect to see more risk seeking, and we do. So this lines up with Salience Theory's predictions.
All right, for example C, what we're going to do is we're going to say you start with a chance at a sure thing at $100, or you can have a 50% chance at 0, or a 50% chance at 200. Right? So we have a 50-50 chance at gaining 200, or a 50-50 chance at 200 or 0, or a sure thing of 100, right? And so we can go ahead, put this into our gain salience function here, right? And we can go through and we can say, okay, well, what do we need? We need to figure out the gain, the loss, and the reference point. The reference point is the sure thing, which is 100. And then we see, okay, if we got the gain, how much did we change from the reference point? If we got the nice payoff, we get 200. How much did that change from the reference point of 100? Well, it changed 100. And how much did, if we got the bad outcome, how much does it change from our reference point of 100? The bad outcome is 0. How much did it change from the reference point? Well, it would change 100 also. So this one's going to have some pretty easy math to go through here, right? So let's do our gain salience function first, right? So if we go through and we look at our gain salience function, we plug everything into here, we would have 100 over 2 times the reference point of 100 plus the gain, which is 100, right? And then we could go back and we could say, okay, let's do this loss salience function. We can put in 100 is our L over 2 times our reference point of 100 minus our L, which is, again, 100. If you go through and you do the math for this, right, in the gain function, you end up with 1/3. And in the loss function, you end up with 1. You take the absolute value of these to see which one is larger. all positive values here, so which one of these two is larger? The loss salience function is larger, so we're going to be loss salient.
In example C, the loss salience function is greater than the gain salience function, so losses are more salient. With loss salience, we increase our risk aversion, which increases the chances that we choose the sure thing. Here you can check your math for example C.
All right, here in example D, we're going to start dealing with some negative numbers. So here, there's some bad things that are going to happen, right? So we have a sure thing at losing $9,000. Or we can say, you could take a gamble, and there's a 10% chance that you'll break even, that you'll have nothing, or a 90% chance that you'll lose even more, and you'll drop down to negative 10,000. Right? So here we want to look at, okay, well, what's our reference point in this consideration? What's our reference point? Our reference point is going to be this negative 9,000 that we could get for sure, right? But then we want to look at our loss, and we want to say, what's the difference between our bad outcome, our worst outcome, and the sure thing? And the difference here is actually $1,000, right? The difference between those two is $1,000. So we're looking at a loss the size of 1,000. Then we also want to say, well, what's our gain? So what's the difference between our good outcome and the sure thing? And the difference between those two things is $9,000. Okay, so we can go through and now we can plug this into our various functions. So our gain salience function and our loss salience function. So let's start with the gains. So what we would do is G, which is 9,000 over 2 times our reference point of negative 9,000 plus the amount of the gain, which again is 9,000. Right? And now let's plug into our loss salience function. So L, the loss, which is 1,000 over 2 times the reference point X, negative 9,000, minus our loss amount, which again is 1,000. If you go through, you do the math here, we will end up with negative 1, and we will end up with negative 0.053. All right. So in this case, what we have to do to make our comparison to see which one is more salient, which one stands out more, we have to take the absolute value of our outcomes here of the gain salience function and the loss salience function and see which one of those is larger. So we drop the negative sides for both of those, and it ends up being that the 0.053 is going to be smaller than the 1. And so we here are going to have gain salience. The gain salience function is going to have a larger absolute value.
In problem D, the loss salience function's absolute value is less than the gain salience function's absolute value. Gains are more salient than losses then, so we have gain salience. Gain salience increases risk seeking and thus makes us more likely to choose a gamble. Once again, check your work. We can see that we're gain salient, which makes us more risk seeking, which makes us more likely to choose the gamble.
Similar to the last example, we're in the loss region again. In the last example, however, the relative gain was really big, whereas the additional loss was really small. Here we're going to have something a little different. So let's look at this gamble. You have a 1% chance at losing $1,000 and a 90% chance at losing $900. And you also have the option of a probability of 100% chance at losing $910, right? And so our cool payoff, our great payoff, if we're happy, is going to be this negative $900, right? And our bad payoff is going to be, if we get that, minus 1,000. So if we go through and we say, okay, what's our reference point, right? We can fill in for our X here, and we're going to get this negative 910. And then we want to say, okay, we also need to figure out our L, right, which is the difference between the really bad outcome and our reference point. So the difference between these two is a difference of 90. Our gain, what's the difference between our good, our best payoff from the gamble, and our sure thing reference point? What's the difference there? G is equal to 10. Right? So then we can go through and we can plug into our salience functions here. So we can say 10 over 2 times the reference point of negative 910 plus 10, our gain. Or we can look at the loss salience function, and we can say, okay, what's the loss? 90. 2 times, what's our x? Negative 910. Minus our loss of 90. And then we can go through, we could do the math here. I extended these out a little bit just so you can see, but we have a 0.006, right? And then we have a, I'm sorry, that's a negative 0.006, right? And we have a negative 0.047. All right, and now what we have to do at the end is we have to look at the absolute value of either our gain and our loss and see which one has a bigger absolute value, right? In this case, the absolute value of the loss, right, is a larger number, right? We have in the tenths column here, right, versus into the hundredths column here. So the absolute value of the loss is bigger, so we have loss salience. We have salience in the category of loss.
And here we have problem E's results, where we have the loss salience function being greater than the gain salience function, which means that we are loss salient. When you have loss salience, this increases risk aversion. When you have higher risk aversion, you're more likely to choose the sure thing. And once again, you can check your math here, but we have loss salience, which increases risk aversion, which makes you more likely to choose the sure thing.